Let's do exam solutions. Happy Tuesday. Look, if you're a student in Calculus 2 and you don't know how to graph sine of x, then you're doing learning wrong. This should be something that you can readily graph without much work. We're interested in what happens between 0 and pi. So let's say pi is here. Let's say this is height 1. So the sine curve it's 0, it starts, and then it comes up at pi over 2, and then it comes back down, and then it goes like this. But what we're interested in is we're interested in this particular region right here. So we're going to do two things. We're going to rotate it first about the x-axis, and then compute the volume of that solid, and then we're going to rotate it around the y-axis and compute the volume of the solid. So I'm going to sketch these real briefly, but if you rotate about the x-axis, it's going to give you a shape like this. And of course, this is a three-dimensional, sort of almost like a football. It's not a football, but it sort of resembles it. And so when we rotate around the x-axis, what we notice is the cross sections, if we take vertical cross sections, that we get circles. And so that means that the disk method is most I don't want to say most likely to work. It will work, and it's going to give you the easier computation. So we'll use the disk method here. So since the vertical slices are disks, we're going to use that method. So what do I mean by vertical slices? Well, what I mean is if I look at, for instance, if I take a slice of this object, and if I think about it, this slice is a disk. It's a circle. And again, you're going to need a little bit of an imagination, but you gotta give it. Okay, so what does the disk method say? The disk method says that this solid has a volume of integrate 0 to pi, and then it's pi times the function squared. So it's going to be sine x quantity squared dx, which becomes pi times the integral of 0 to pi of sine squared x dx. And how do we integrate even powers? We integrate even powers using this half angle formula. So it's pi times 1/2 integral 0 to pi, and then it becomes 1 minus the cosine of 2x dx. And so we have a pi over 2 out front. When you integrate 1, you get x. When you integrate the cosine, you get 1/2 the sine of 2x. And this is evaluated between 0 and pi. And so when you plug in the bounds, when you plug in pi, you get pi minus 0. And then when you plug in 0, you get 0 minus 0. So your final answer is 1/2 pi squared. That is the volume. So take a moment to think about this particular situation, and let me know if you have questions or comments. Nothing. All right, so that's the volume of the shape we get if we rotate the original region. If I take this region and rotate it around the x-axis, I get this solid, and that's the volume of that solid. Okay, now we want to do the next piece, and the next piece says let's rotate around the y-axis. So if we do this, we get a different shape or a different solid. And so that solid's going to look sort of like a donut. So let's try to see if we can sketch it. So remember, you start with this region like this. And so when you rotate it, it's going to give you this sort of mirrored image. And then it's going to have this. So it's kind of like a volcano donut type thing. And again, it's not super easy to draw this, so it's going to have some sort of like, three-dimensionalness to it. And again, it's not the easiest to draw. But a good way to try to help sketch it, and maybe you can have a better sketch than I have, is if you go back to the original region and you take a strip, a vertical strip. Say I take this piece right here, and I ask what happens to this green strip when I rotate it about the y-axis. And what it does is it comes out and around, back into the whiteboard, and then back through the whiteboard and around. And so what you end up getting is you end up imagining that it looks something like this. You get what we call cylindrical shells. So the shell method says that the volume is integral 0 pi of 2 pi x times the function, which is sine of x. Now this integral requires integration by parts. So this is 2 pi, the integral 0 to pi of x sine x dx. And so the proper way to do this integral is to set u equal to x, and that means your du is dx, and then you set dv equal to sine x dx, and so your v is negative the cosine of x. So again, the product of x times the sine of x means that I'm using integration by parts formula. So when we do this, we're left with 2 pi, and then what do we have? We have uv, so this is negative x cosine x from 0 to pi. And then it's minus the integral from 0 to pi of v du, so it's cosine x dx, but the minuses multiply and give us a plus. Now, if you've done enough practice, you'll recognize a couple things. First off, the integral of cosine from 0 to pi is 0. So if you can work it out if you want to, but this thing is equal to 0. You should check it out for yourself. And then when you plug in pi, this becomes 2 pi, negative pi, cosine of pi, and then of course it's going to be minus 0, so we get rid of that. And then cosine of pi is negative 1, so now you get, interestingly enough, positive pi, so here you get 2 pi squared. So again, if you have a question, please feel free to ask. questions, comments? Okay, let's move on then. So that was problem 1. So for 2, we have to do 2 integrals. The first one is this creature. So we talked about integrals of this type. If you have the product of sines and cosines, there's a few ways you can go. If you wanted, there's what's called, there's these formulas that we discussed that you can use if you know how to apply them. But I'm going to just do it from scratch. And the odd power of cosine tells me that I am going to write it like this. Cosine squared x times sine to the 4th x times cosine of x dx. So I'm going to break the odd power up. And then I'm going to replace the cosine's odd power, or excuse me, even power with 1 minus the sine squared. So I'm just using a trig identity. But if I do this properly, it sets this integral up very nicely, because now it's an elementary substitution if we've done this problem correctly. So what's the substitution? Well, come over here and put it in. U is going to be the sine of x, and that means du is cosine of x dx. And then when u is 0, you get x has to be 0. And then when u is pi over 2, excuse me, I wrote that down wrong. Hold on a second. Dyslexia. Although I shouldn't joke about that. But I had it backwards. I should flunk the text. When x is 0, what is u? Well, that implies that u is equal to 0. And then when x is pi over 2, what's the sine of pi over 2? The sine of pi over 2 is 1, so that implies u is equal to 1. So when I do this change of variable, this substitution, this reduces to integral 0, 1, 1 minus u squared times u to the 4th du, which is now a very elementary integral. So if you integrate this properly, you get 1/5 minus 1/7. And then 1/5 minus 1/7 is 2/35. So let's make sure I didn't make an error. If anybody has a question or a comment, please speak now. It's possible we make errors, you never know. Does anybody have a question? Anybody find an error? You shouldn't find any errors because that is indeed correct. Does anybody have a comment, question? So I highly encourage you, even if you feel like you got these correct, to work these out again on your own. It's how you learn. Okay, so we move on. All right, so the next integral was this creature. a indefinite integral, x cubed over 9 minus x squared. And so what we're going to use here is you're going to use a trig substitution. The 9 minus x squared tells me I should maybe think of putting x as 3 sine of theta, which means dx is 3 cos theta d theta. And so when you plug this in, the substitution, you're left with 3 to the third, which is 27 sine cubed. And then downstairs, you get 9 minus 9 sine squared. And you have times 3 cos theta d theta. And then lots of this stuff is going to sort of cancel out. The reason this substitution works is because what happens downstairs is this just becomes the square root of 9 cosine squared. And so the square root will be eliminated because all this stuff, this goes with this, and then this goes with that. And so it simplifies down to 27 times the integral of sine cubed theta d theta. Now, once again, like we had in the previous problem, is we have a trig function raised to a power. And one of the standard ways to do this is to do the even odd trick that we did before. Write this as 1. So you can write this as sine squared times sine. So this is 1 minus cosine squared theta times sine. So it's the same trick we did in the previous problem. And now you do a substitution. So this problem already has required 2 substitutions. So what substitution am I going to do now? So now I'm on my third variable. Well, now I'm going to let u equal cos of theta, and then du is negative sine theta d theta. Which means this becomes 27 integral 1 minus u squared du, but we have a minus sign, so I'll pull that out front, and then you have your du. And of course, this is now easy to integrate. It's negative 27, and then this is going to be times u minus 1/3 u cubed plus c. So let me clean that up. It's kind of ugly. I'm squeezing it in there. We're going to So this is, again, this is a pretty challenging integral. Okay, so we're not done yet. So we have to notice that we can rewrite this. This is, if I multiply the negative sign through, I can think of this as 27u, or excuse me, negative 27u plus 9u cubed plus c. Let's just double check that. Negative 27u plus, right. 27 over 3 is 9, u cubed, and then, of course, our plus c. Okay, but we're not done still because this is in u, and we don't want to be in u's. We need to go all the way back to x. So the first thing we have to do is get back into from u to theta. So since u is cosine, this becomes negative 27 cosine theta plus 9 cosine cubed theta plus c. And then we have to get all the way back to x. So let's remember what all this was happening. Our triangle that we have, we had theta. And what was theta? Well, we started with x equals 3 sine theta. That's what we started with. So that makes this x and this 3. Excuse me, that's not correct. Makes this 3. Sine is opposite over adjacent, or excuse me, opposite over hypotenuse. And then by the Pythagorean theorem, we know that this is nothing more than 9 minus x squared in the square root. Okay, so we want to know the cosine of theta. So what's the cosine? Cosine of theta is adjacent over hypotenuse. And so if we plug that into our expression on the left, we're left with negative 27 times this over 3 plus 9 times this creature cubed plus c. Which we could clean up if we wanted. Negative 9 times this. And then 9 over 27. So this is the same as 1/3. And then you can write this as, if you wanted to clean it up, I guess you could write it like this. Does anybody have a question or a comment? This is a tricky computation, but it is one that you should know how to do. Comments, questions? All right. So let's move on to number 3. So 3 deals with this integral. And the first thing we want you to do is approximate it using a Wright-Riemann sum. So let's sort of make sure we all understand what we mean by that. So perhaps the best thing you could do is look at the graph. I can't get my marker. So if I look at the graph of this creature, it's going to look like this. We're only interested in what's happening from 0 to 1. So whoops. So we know it goes through this point 0. When I plug in 0, I get 0, comma 1/4. And then it graphs, the graph comes up like this. Of course, it does the same thing over here. But we're just interested in what's happening on 0, 1. And so turns out there is a vertical asymptote at plus and minus 2. So what we're really interested in is we're interested in this piece right here. So say this is 1. We want to use 6 rectangles to approximate this. So if I do it like this, this gives me 4. So how do I get 6? So to get 6, I need to break 0, 1 into 6 pieces. So the first piece would be 1/6, then 2/6, then 3/6, and then 4/6, and then 5/6. And then I get 6 equal pieces. So we call this number our delta x. And what we know from the definition of the integral is we know that, and by the way, this is my x1, my x2, my x3, my x4, my x5, and then this is my x of 6. We know that the integral we care about is approximately delta x, and then we have to plug the expression, each one of these 6 guys, into the expression. My length, think about your rectangles. Here's a right Riemann sum. Looks like this. That's 4 rectangles. We asked you to do 6, though. And so what's the height of each one of these rectangles? Well, it's going to be 1/4 minus 1/6 squared plus 1/4 minus 2/6 quantity squared. And of course, you have to do this all the way out to the last one, which is 1/4 minus 1 squared. Now, you can do this by hand if you want, but one of the things I told you before is you can do it using a calculator. And so if you use a calculator to do this, it becomes a little easier. One way to do it is to use Desmos. It makes it real easy to plug these things in, and it computes it real quickly. No matter how you do it, if you do it properly, here's what you'll end up with. I gotta get my marker. And let me just double check my arithmetic. So if you do it, you should get approximately 0.28211. So does anybody have a question about this first portion of this problem? Going once, going twice. So our approximation using 6 rectangles gives us 0.28211. And if you draw the graph, that actually looks very plausible. It looks like we're on the right path. Okay, so the next part was then to use the following technique. Now we can do it exactly using the following technique. Similar to what we did earlier, we're going to let x equal 2 sine theta, and then dx is 2 cos theta, d theta. And so this becomes the integral of 1/4 minus 4 sine of x, 4 sine squared of theta times 2 cos theta d theta. Now, what are your bounds? Well, your bounds, when x is 0, this has to be 0. When x is 1, this is pi over 2. And then, of course, this simplifies to 4 cosine squared theta times 2 cos theta d theta. And now you have to integrate 1 over the cosine. Which is the secant. Now, on the previous homework, we asked you to compute the integral of the secant. Now, what happens here? First off, does anybody spot an error?
Professor?
Yes.
Why did it go from 0 to 1 to 0 to pi over 2? Did we find new bounds, or?
Well, yeah. So let's first off, that's where the error is. Let's think about that. So exactly, when you do a substitution, you need to change your bound. So let's look at there's an error here. So the first thing I'm going to say is I'm going to delete these things because that's incorrect. So the correct way of doing this is saying, okay, let's look over here at my thing. What happens when x is equal to 0? When x is equal to 0, I have 0 equals 2 times the sine of theta, which is the same as 0 equals sine of theta. So what value of theta solves that equation, Tom? Well, if you want to solve that solution, you need to have theta equal to, this right here implies that theta has to be 0. Now do the other bound. What happens when x is 1? Well, when x is 1, you need to solve 1/2 equals the sine of theta. Now this one, again, solving these trig identities are little trig equations are much easier if you remember your unit circle, but most of us don't remember our unit circle, which is not good. We need to remember that. So it turns out, what is the sine? What angle has a sine of 1/2? And it turns out that it's pi over 6. Now, if you don't do that from your unit circle, another way of getting that number is to just go to a calculator. If you just go to a calculator and ask it to solve the arc or the inverse sine of 1/2 on your calculator, it will tell you exactly what it is. Does that make sense? Good. Okay, so what that means is our bounds should be 0 to pi over 6. 0 to pi over 6 and 0 to pi over 6. Okay, so how do we solve this problem? Well, we have to go back to our homework or our book, or if we want to torture ourselves, actually compute it itself. But you don't have to do that because we told you what the integral was already. The integral of secant is the natural log of secant theta plus tan theta. And we are evaluating this from 0 to pi over 6. Now, when you plug in pi over 6, which is nice here, is you have log. So what's the secant of pi over 6? What's the tangent of pi over 6? Well, these are things that you could easily look up if you don't remember them. And what's the secant? So, you know, if you plug this in, you have secant of pi over 6 plus tangent pi over 6, and then that's minus what happens when you plug in 0. So that would be log of the secant of 0 plus the tangent of 0. And if you go and look up these values, what you end up getting is you get this all adds up to 1/2 the natural log of 3. Oh, I'm sorry, 1/4 the natural log of 3. I forgot that thing out front here. Hold on, we have these extra 1/2s. Where did it go? I keep losing my eraser. Ah. So this extra 1/2 out here, what we end up getting is if we do the arithmetic properly, you're going to get 1/2 times 1/2, so you get 1/4 the natural log of 3. Now, if you compute that number, if approximated on a calculator, you're going to see it's very close to what we got in part A. All right, does anybody have a question about this?
So for a couple of these, I've gotten the same answer, but I haven't, whenever I did a substitution, I didn't change the bounds. I just kept the same bounds and then.
Right, but then you didn't plug it in until afterwards then, right? So once you
Right.
integrated, you switched back to X, I assume, right?
Correct.
Yeah, that's okay. That's fine, but you just got to remember to do that.
Okay.
If you don't remember to switch back, then you're going to get the wrong answer. Right?
All right.
Does that make sense?
Yep.
Yeah, that's just, we talked about that actually a few weeks back. You could definitely do that. I just prefer to switch my bounds. That's just my preference. But you don't have to do it if you don't want to. As long as you keep everything in order and you don't make things up, create your own math, Paul, then you're fine. Does that make sense?
Yep, all good.
All right, great. All right, so now let's do it the other way. So we asked you to do this 2 different ways. So now we want you to do this integral, but we want you to perform it or solve it a different way. Now we want you to recognize that 1/4 minus x squared is the same as 2 minus x times 2 plus x. Difference of squares, right? So that's some elementary algebra. And then we want to write this as a over 2 minus x plus b over 2 plus x. And we want this stuff to be the same. So by partial fractions, this means I have to have 1 equal to 2 plus x times a plus 2 minus x times b. And we do this thing called matching coefficients where we're going to rewrite this now. I have 2a plus 2b, and then it's going to be ax and negative bx. So it's going to be plus a minus b times x. And so this tells me the only way that this is true is if 2a plus 2b equals 1 and a minus b equals 0. That's the only way this is true. So we talked about this. We've done a few examples. This is called the partial fraction decomposition. anybody have a question about this piece? So we didn't do any integration yet. We just are finding the partial fractions. And so this tells us A and B, excuse me, let me be a little more careful. What does this tell you about A and B? Well, it tells you that A and B have to be the same number. That's the only way it can work. And then what number do they have to be? Well, if A and B are the same, from the top equation, you get that they have to both be 1/4. So if you solve this system of equation, what you end up getting is that A and B both have to be 1/4. That's the only way it's going to work. Yes or no? Yeah. And you could check this for yourself. So what we've discovered is the following, here's what we can conclude. That 1/4 minus x squared is the same as 1/4 over 2 minus x. Getting sloppy. So this is a 1/4, and then it's plus 1/4 over 2 plus x. Now you can check this for yourself if you want. Does anybody have a question about this? Okay, if that's the case, then the integral we're after, the integral from 0 to 1 of 1/4 minus x squared dx, is 1/4 this integral plus 1/4 this integral. Now, both of these integrals, you know, they don't necessarily, well, they require substitution, but some people will do it manually because they've done it enough times. So I'm going to do 2 substitutions just to make it very clear. On the first one, I'm going to set u equals 2 minus x. And so du is negative dx. And then my bounds are going to change. So when x is 0, when x is equal to 0, that implies that u is equal to 2. And when x is 1, that implies u is equal to 1. So this first integral can be rewritten like this. It's going to become negative 1/4 the integral from 2 to 1 of 1/u du. And then for the other integral, I'm going to make a substitution as well. I'm going to set y equal to 2 plus x. And so dy is just dx. And when x is equal to 0, that implies y is equal to 2. And when x is equal to 1, that implies y is equal to 3. So that means this second integral is plus 1/4 the integral from 2 to 3 of 1/u, or excuse me, 1/y dy. So I'm not saying this is the only way to do it. There might have been another way for you to reason these substitutions, but this is how I want to do it. And so if I'm very careful now, I can do the integration. This is negative 1/4, and this becomes the log of 1 minus the log of 2. And then it's plus 1/4, and then this is the log of 3 minus the log of 2. And so there's lots that happen here. For instance, the log of 1 is equal to 0. So that goes away. I have a minus log 2, so that adds up to 0. And the only thing that survives is the log 3 term. So if you want to be specific, you get log over 4 log 2 plus log over 4 log 3 minus 1 over 4 log 2. And the final answer is what we found previously, 1/4 log cubed. Just like we got the alternative method. Whew, a lot happening here. Does anybody have a question? Does anybody want to put out a bounty on my head because this problem was too hard, or you think it was unfair? Fun times. So you'll notice we got the same answer 2 different ways. We got log 3 over 4 using a trig substitution, and we also got it using partial fractions. So essentially, we drove to grandma's house 2 different ways. Now, you can decide which one was easier. Okay, any questions before we move on to number 4? Okay, so number 4 is another interesting problem. So we're going to study this integral. And why is it equal to the log of 2? It's equal to the log of 2 because by definition, the antiderivative of 1 over x is natural log of x from 1 to 2, and that equals log 2 minus log 1. But as we just already said, log 1 is 0, so you get log 2. That's one way to think about it. So now what we're going to do is we're showing you that you can approximate the log 2 without using a calculator. You can use integration to do this. So let's draw the graph of this function, 1 over x, which looks like this if we sketch it. And we're gonna just draw this not to scale because we're trying to get some information, but let's say that this is the point 1. And so here's what we know. We know if that's 1, then we want to use what? 4 things. So I'm going to break this into 4 equal pieces. This is 1/4. This is 1/2, and this is 3/4. And so what I'm suggesting is if I look at this region from here, so what's this point right here? Well, this is the point 1/4, comma 4. And this is the point 1/2, comma 2. And this is the point 3/4, comma 4/3. And this is the point 1, comma 1. And so the purpose of this problem is for you to make a connection here. You can use these points to draw trapezoids. In particular, I can draw, if I get be real clear here. If I draw this line and then this line and then this, now I have a trapezoid. And then if I do this, and then I do this, whoops. Stop moving. If I do this, I have a trapezoid. And so I think you get the idea. Hopefully now, the point I was trying to make is we could do this with, here I have 3, in the test I told you to do 4, so I mean, I could do 4 if I wanted. Oh, I forgot. No one yelled at me. What is happening? I hate not being in front of you guys. What is wrong about this? Everything. I'm not even studying the thing I want to study. So let me fix this. What was the error of our ways? take my eraser. We weren't interested in 0 to 1. What are we interested in? We're interested in what happens from 1 to 2. So let me fix that. I apologize about that. That was an actually honest mistake. So we're interested in what's happening from 1 to 2. So if let's redraw this picture. Comes down and looks like this. Whoops. And so let's say this is the point 1 right here. And this is 2, so let's call this 1. What we're interested in is we're interested in approximating this region under the curve. This is what we want. This region. And so why do we want this region? Because that region, the area of that region is the value of the integral, which we know is log 2. And so the idea is, okay, take this region and let's approximate it using, instead of rectangles, let's use trapezoids. So in particular, I said, let's get 5 of them. So if we take our eraser here and let's just, or get a different color, let's get a, let's say, I don't know, green. I want to get 5 trapezoids. So, or I keep saying 4 trapezoids. Losing my mind. So how do I get 4 trapezoids? Well, I have one, say, here, and then the second one have that base. And then this will be my third one. And so, or if I want, I could say, let's make them all equally spaced. I didn't tell you specifically how to do it, but let's just do this. Let's call this, 3 halves. You can, however you want to do it is up to you, but we're trying to think of a simple way to determine these points. So if I construct this trapezoid like this, and then I construct this trapezoid, and then I construct this trapezoid. The idea is to notice that the area of the 4 trapezoids closely resembles, or at least approximates, the same region that's shaded in red. And so what are these points? Well, this is 1, 1. This is, so what, if this is, here's an easier way to do it. If you want, this is 2, 1 half, right? And then what's the middle point? The middle point is 3 halves, 2 thirds. So the only ones that, aren't so obvious are, what are these points? Well, if you think about how I constructed them, I am taking the point 1 and I'm adding a quarter to it. So that's 1 plus, 1/4. Right? So if you want to think about what these things are, in specifically, this is 5/4, 6/4, and then that's 7/4. And so all that remains for you to do is understand what is the area of a trapezoid. Well, you might not remember what it is. You can either deduce it or you just look it up. I mean, I think if you Google it, it tells you the formula right away. So anyhow, if you think of it that way, let's call this guy T1, T2, etc. So what's T1? Well, what's the area of that trapezoid? Well, the way it works is you take the 2 y coordinates, which is 1, plus the y coordinate here. This is 5/4, 4/5. So this would be over 4/5, all over 2, and then times the width. Well, the width is 1/4. And then T2 is it's going to be the 4/5 plus the next height, which is 2/3 over 2, all times 1/4. Etc. So if you do that for all the pieces, you can add them all up using a calculator by hand. I don't know how you want to do it. Does anybody have any questions about this so far? Comments, concerns before we spit out the answer? Is anybody chatting? Even check the chat. Okay, so anyhow, if you do this, if you compute the, you add up all 4 areas, what's it give? It gives the disintegral so the log of 2, which we know is equal to this integral, is approximately T1 plus T2 plus T3 plus T4, which if you add them up, you're going to get 0.697 024 if you carry out that approximation. So that was the purpose of the problem. And if you go to a calculator and ask a calculator what log of 2 is, you're going to see that it's 0.693. So we approximated it to 2 decimal places. And so that was the point of the problem. Does anybody have a question about this? Comments, concerns? All right, so then let's move to the last problem, which wants us to study this creature. So look, you could kill all these birds with one stone, and so that's kind of how I'd like to do it. I'm going to integrate this, and this thing requires parts. So I'm going to sort of kill a few birds with one stone over here. So you're going to let u equal t, and then your du is just dt, and then you let dv equal e to the negative t dt, and so v is minus e to the negative t. So if you do this, you get uv, so it's minus t e to the negative t from 0 to x, and then it's minus the integral 0 to x of negative e to the t, negative t, so it's just this. Now, when you plug in the upper bound here, you get negative x e to the negative x, and then when you plug in 0, you get 0, so that's minus 0. And so if you integrate this guy that's left, you get minus e to the negative t from 0 to x. So plug this in, you get So if you simplify this creature, here's what you get. So I did the hard part. So what I really just did for you is I did part B. Because if you do part B right away, then you get part A for free. Now, of course, this is a complicated argument. So what I tried to do is walk you through it. I asked you to do the special cases, and then hopefully you see the pattern, and this is the pattern. So, I mean, you can easily go to a calculator if you wanted, but here's what we learned right away. We know f of 10 is negative 10 e to the negative 10 minus e to the negative 10 plus 1. You know, f of whatever, you know, f of 100 is negative 100 e to the negative 100 minus e to the negative 100 plus 1. And by the way, what you're going to see with all of these is these are approximately 1. That's the point of the problem. And so since this is an expression in x, we can take the limit as x goes to infinity. And so if you take the limit of this, negative x e to the negative x minus e to the negative x plus 1, this limit equals 0 minus 0 plus 1, which is 1. Now, there is one subtlety. This limit, the first piece, this first limit requires L'Hopital's rule. So it's not obvious, or it shouldn't be. So, and you might want to review this. So you might want to review L'Hopital's rule and see why that's the case. But that was the purpose of this problem. Does anybody have a question about this? Comment, concern? Going once, going twice, 3 times, 4 times. Some of you mad, you're like, oh my God, I did this wrong. Or some of you are like, what? That test was hard, it's unfair. Any questions, comments, concerns?
Was the answer to 6C RZA?
Ha! It is. That's the RZA. Very good. See, you're learning. Very good. Yes, it is the RZA. Very good.
Oh, it's RZA, not RZA?
Well, it's pronounced RZA, but yes, it's RZA is the spelling for sure.
All right.
So he's a rapper. The Wu-Tang Clan. Come on, Paul. These are the things I have to teach you. We have to get you some cultural education as well. And
I mean, they did kung fu fighting, didn't they?
well, they didn't do that, but they're big into like incorporating kung fu culture into their music. Yes.
Okay.
Yeah. So there's the RZA and the Jizza. See, you learn something new every day. That's what I could ask you. Name the members of the Wu-Tang Clan. Very good. Okay. Any other questions? By the way, I hope to have your grades updated sometime tonight or tomorrow at the latest. But if you want it to be sped up, you can email me and keep saying, please post our grades. And then I'll eventually do it because of the squeaky wheel gets oiled, right? All right. Any questions, comments, concerns? All right. Well, listen, I'm going to, we'll get back on Thursday. Thank you guys for joining, and I will talk to you Thursday, unless you have questions and need anything else. All right. All right, everybody. Take care. Thank you. Be safe.